We start our exposition of graph convolution filters by first formally defining what graphs are. And we do this by looking at so-called directed graphs. Directed graphs are triplets. G, that stands for graph, is a triplet of a vertex set V, an edge set E, and a edge weight set W, where the vertices, here in blue, are sometimes also called nodes, are defined as a set of n labels. So the vertex set is the set of integers from 1 to n, where n is the number of vertices, in this case 5. Edges are ordered pairs of labels ij, and we interpret in the context of graph convolutions ij, the edge ij, as the node I being influenced by the node j. So the intuition is a little bit the opposite of how graphs are normally defined. And we'll see this also in terms of how the arrows are oriented. And the weights that are associated with each edge, wij, are real numbers that are attached to these edges, and that determine the strength, the interaction strength between two nodes. In particular, wij determines the strength of the influence that node j has on node I, but not the influence that node I has on node j, which would be wji. That's important. We draw such a graph by drawing arrows between vertices, where arrows are always drawn from node j to the influenced node I for an edge ij. So for example, here we have an edge 1, 2 that is represented in this graphical illustration by an arrow from 2 to 1. We don't have an edge 2, 1 that would be represented by an arrow from 1 to 2. But this may be a little bit counterintuitive definition of influence makes sense if we look at the matrix algebra later on. So the only thing we need to keep in mind here is that the arrow indicates the direction in which the influence is executed. So node 2 has an influence on node 1, which means that if we execute these graph operators that we later define, that means that some of the information, some of the signal that was present in node 2 gets transferred to node 1. It's also important to note that edge ij is different from edge ji. In a directed graph, we can have, for instance, edge ij, as in the case here, but not edge ji. In some cases, we might have both, but we don't necessarily have to have both. Both are possible and both are different. If both edges are part, like the edge from I to j and the edge from j to I, are part of the edge set, their weights can still be different. In a directed graph, there is no restriction that the weight from edge, the weight 5, 3, and the weight 3, 5 are the same. Okay. A graph is called symmetric or undirected sometimes as well if the edge set and the weights are symmetric. And the edge set is symmetric exactly if ij, the edge ij, being part of the edge set implies that also the edge ji is part of the edge set. And we indicate this here in this graph by simply having two-sided arrows. So all of the connections that we draw in such a graph are two-sided arrows now. Either we have no connection, like here in this case between 4 and 5, or we have a connection from 3 to 5 and from 5 to 3 as well. And furthermore, not only both edges are there, but in this case also the weights are symmetric, which means that wij is the same as wji. There's basically just one value at this edge, and that acts in both directions. Furthermore, a graph G is called unweighted if it doesn't have weights. Equivalently, we can say that all weights are 1. And this is the typical way of formulating this, and we are going to have a look at some of these examples in the following slides, just because weights of 1 are simple to work with. In this case, the graph structure just tells us what is close in terms of the edge connectivity, but each edge doesn't contain any additional information on how close two nodes are with respect to each other. If we look at this particular edge compared to two other nodes that are directly connected by an edge, but that could have, in the case of a weighted graph, could have a different weight. So here, all the weights are the same. wij is 1 for all ij edges in the edge set. Unweighted graphs can be either directed or symmetric. But most graphs we encounter in practice are actually weighted. For many problems that we will see, we have weighted graphs, and if we have this weight information, of course, we should take it into account. This is part of the prior knowledge, as is the graph structure. So the more prior knowledge we can take into account into our computations, the better, hopefully, our predictions are. So we'll see symmetric or directed graphs, and most often they will have weights in practice. Graph shift operators. This is now the transformation. We're going to talk about the transformation that operates, that defines a graph. That is the mathematical formulation of a graph. And there's multiple options to define this, but they are all derived from the graph structure, from the vertices, the edges, and the weight set. The first shift operator that we define, all of these operators that we're going to define here are shift operators, as we'll see in the end. The first operator that we define is the simplest one, which is just the adjacency matrix. So here we have a symmetric graph. In this case, it's an unweighted symmetric graph where we have just weights 1 or 0 if there is no connection between nodes. And the adjacency matrix of a graph G is then the sparse matrix A with non-zero entries exactly at these elements where we have a weight defined, where we have an edge defined. So Aij, this is indexing into that matrix at element ij, is equal to wij, the edge weight, exactly when we have an edge in the edge set. So for instance, for this graph here, we have an edge between 1 and 2. This is the green edge, so we have a 1 here at this location, which is in the first row and the second column. Similarly, because it's a symmetric graph here, we have a 1 in the first column and the second row. Right? W12 and W21. And the same holds, for instance, for this blue edge here, where we have a 1 here in row 1 and column 3, and in column 1 and row 3. So if we continue this process and filling in ones based on where we have edges in that graph, we get this matrix. And all the remaining locations are 0. And this is called the adjacency matrix. If the graph is symmetric, as in this case, we immediately see that the adjacency matrix is also symmetric. In other words, A equals A transpose, or the matrix here is symmetric at this axis. The next thing we're going to define are neighborhoods and degrees. So we'll consider this graph here in this example now. The neighborhood, which you call here n of I of node I, is the set of nodes that influence node I. So mathematically speaking, n of I is the set of j's for which the edge ij is in the edge set. Remember, we have said that for any edge with any I, for any edge ij, j is influencing I. So we need to look at the entire edge set and need to look at the edges that have j that have I as the first component, and then we accumulate all the j's into this set, and this is the neighborhood. This is the set of all the nodes that have an influence on node I. In this example here, we have these two green arrows that indicate that both node 2 and node 3 have an influence on node 1. But there is no edge from node 4 to node 1, and there is no edge from node 5 to node 1. Therefore, the node 1 neighborhood is the set 2 and 3. The two vertices 2 and 3. The degree di of node I is then the sum of the weights of its incident edges. So we have a weighted graph here. And in this particular case here, we would sum up the values W12 and W13 to get the degree of node 1. In the case of an unweighted graph, for instance, we would have a 1 here and a 1 here. So the degree of that node 1 would be 2. In other words, the degree specifies how many nodes and how strong they have an influence on that particular node we want to compute the degree for. This is the neighborhood and the degree of a node I. Now, the degree matrix D is a diagonal matrix where we put these degrees at the diagonal. So we have, in this case of an unweighted graph here, we have 2 for node 1, we have 3 for node 2, because there's 3 incident edges, one from node 1, one from node 3, one from node 4. We have 3 for node 3, because there's also 3 incident edges. But we have just 2 and 2 for node 4 and 5, because there's only 2 incident edges each. And it's 0 everywhere else because it's a diagonal matrix. We can also write D in terms of the adjacency matrix. And this is very simple. So we can write this as D equals the diagonal matrix of the vector A, where we multiply the matrix A with the 1 vector. If we look back at the adjacency matrix here of this same graph, if we consider a 1 vector here multiplied with this matrix, then we're in the first element we're getting a sum of these two elements, which is 2. In the second element we get the sum of these 3 elements, which is 3. And so we arrive at the same matrix. Stack operator here just indicates that we're taking a vector and converting it into a diagonal matrix. This is the diag operator. Now, the next graph shift operator, so these haven't been graph shift operators, the degree matrix and the neighborhood, but the adjacency matrix was a graph shift operator. The next graph shift operator that we're going to define is the Laplacian. The Laplacian matrix L of a graph with adjacency matrix A is defined as the degree matrix minus the adjacency matrix. So we take this degree matrix here that we have defined here, and subtract the adjacency matrix. In the example from before, we have this degree matrix here, we have this adjacency matrix here, and we have the resulting Laplacian matrix, L, here on the right. And we can already see that the degree is on the diagonal, which makes sense because we have only diagonal elements for the degree matrix, but no diagonal elements or 0 diagonal elements for the adjacency matrix. And the values of the adjacency matrix are negated at the off diagonals. So we get these elements here at the off diagonals with a minus in front. Now this can also be written explicitly in terms of graph weights, which is clear. Right here we just have this written component-wise. Lij is at the off diagonal is minus wij, and on the diagonal it is this sum over the neighborhood, wij. Now the Laplacian matrix on a graph is called the graph Laplacian. And the graph Laplacian has the same properties for a graph than a Laplacian matrix, which is the divergence of the gradient, has on a regular domain. We're not going to go into detail here, but it's kind of it's measuring the smoothness. It's measuring, if I'm taking a vector, a signal, here we're having 5-dimensional signals, right? So this is if we would have a signal on that graph, a signal is a vector that associates one real number with each node in a graph. So here we would have a 5-dimensional vector. If we would multiply a signal with this Laplacian matrix, then if we would have elements, nearby elements that are defined through this adjacency matrix that are differing from each other, then we would get a large value. But if they have a similar value, we would get a small value. So it's measuring something like smoothness or curvature. Now, what we can do is further to normalize both the adjacency matrix and the Laplacian matrix. And this is useful in particular when the graph is very inhomogeneous, when we have some nodes that are very far from other nodes and some nodes that are very close. So if we have some weights that are very large and some weights that are very small, or if we have some nodes that are connected to many nodes in the graph and some nodes that are connected to only a few nodes in the graph. And we can normalize simply by dividing each element by the square root of di dj, the degrees of these nodes. And if we write this in matrix notation, we have the normalized adjacency matrix A bar equals the degree matrix to the power of minus 1/2 times the adjacency matrix times the degree matrix of to the power of minus 1/2. And similarly, we can normalize the Laplacian matrix. And using these normalized matrices as shift operators, as graph shift operators, as representations for the graph, is advantageous in particular if the graph is very heterogeneous. So we're kind of normalizing the influence over the graph. Now, this is one crucial slide. The graph shift operator, this is what we define here, represents any of the graph matrix representations that you have learned about. So in the case of the adjacency matrix, the graph shift operator S is A. In the case of a Laplacian matrix, the graph shift operator is L. In the case of a normalized adjacency matrix, the graph shift operator S equals A bar. And in the case of the normalized Laplacian matrix, the bar shift operator, the graph shift operator equals L bar. If the graph is symmetric, the shift operator is symmetric as well. That's clear. And the reason why we define this graph shift operator so broadly is that while the specific choice of S matters in practice, compare for instance normalized Laplacian versus regular Laplacian, the analysis that we're going to do holds for any choice. So we're going to just consider S from now, no matter what you will use in an implementation. There's different graph shift operators that people are using for different applications, and all are mathematical representations of the graph. They capture the structure of the graph. The adjacency matrix or the Laplacian matrix, which are actually quite related. Their Laplacian matrix is just D minus the adjacency matrix. They both capture the structure of the graph, and they both allow for a, as we'll see, a diffusion process on that graph. So we're just going to consider this general notion of graph shift operator S from now on. We've already talked about graph signals. What are graph signals? Consider a graph with n nodes, in this example 3, and a shift operator S. The shift operator S is directly defined by the structure of the graph. In this case here, we have just these 3 directed edges, so we have only, in this case, we use the adjacency matrix as a simple shift operator. So we have the shift operator that has element 1 here at the first row and the second column, because we have this edge 1, 2 here, where 2 has an influence on 1, and so on. So we consider this graph G with n nodes that is formalized through its, or represented through its shift operator S mathematically. And then we consider a graph signal, which is a vector. In this case, it's a 3-dimensional vector that assigns one real number, one scalar, to every node. And S encodes the expected proximity or similarity between the components of X. Then multiplication with the graph shift operator of the input signal X, the signal that is defined on that graph. This is the input. Also, when we do inference, this is the input to our algorithm. So we're doing a convolution through the graph shift operator, as we'll see shortly, on that graph. And the input is X and the output is Y. So the multiplication of X with the graph shift operator S yields a diffused signal over the graph. Mathematically, we write Y equals matrix S multiplied with the vector X, which is the graph signal, or if we use an element-wise notation like this. And this implements a local operation where values are mixed with neighboring values. What we see here in this example is a very simple graph, and we have 2 examples here of applying 2 different input signals to multiplying those with the shift operator. So here we have the shift operator S that represents the adjacency matrix of this graph, assuming we have an unweighted graph where all the weights are 1. If we assume an input signal 10, 5, 0, we see that after multiplication with this matrix S, we get 5, 0, 10. And this is also what we expect, because in the simple case, we have that node 2 influences node 1, and that's exactly what happens. Node 2 was represented with value 5 before, and now after applying the shift operator, node 1 is represented with value 5. And similarly, we have, for instance, that node 1 influences node 3, so we have this 10 which is now getting transferred. In this case, it's just a simple permutation matrix. It's getting transferred to the 3rd location in that vector. And you can imagine now what happens if you have multiple errors that point to one node. Or in some cases, people even introduce self-errors, like errors that go from the node to itself. Then all this information gets mixed up. In this case, it's just permuted. With every application of the shift operator, it's permuted. But it's still diffused. We're shifting information around in the graph based on how the errors are defined in the graph. In the simple graph, it's just a permutation. Now, similarly, if we take this as an input signal, 5, 0, 10, and multiply with the shift operator, we get 0, 10, 5. So we see again that, for instance, 5, which was at location 1, is now shifted to location 3, and 10, which was at 3, is now shifted to location 2. So we can define, or we can see that this shift operator, in this case a simple adjacency matrix of this unweighted graph, defines a diffusion process where the signal gets diffused over the graph, but with each application of the shift operator, we're just diffusing by one step, by one hop, by one edge. If there's no edge if we would have more nodes here, like let's say there's a 4th node here, and there is a direct edge from 2 but not from 3, we can only pass information from 3 to that node by applying the shift operator twice. With a single application, we can only pass information along a single edge. And that's what graph signal diffusion using the graph shift operator is. Now, as already mentioned, we can apply S multiple times to obtain a diffusion sequence that can be recursively written like this. We have xk, which results in xk plus 1, where x0 is the input. So we define x0 as the input to this diffusion sequence. This is the input signal. Similarly, or equivalently actually, we can write this diffusion process as a power sequence. Say that if we unroll this diffusion sequence here, we obtain a power sequence where, because we have the same shift operator applied at every recursion, we just have xk equals s, the shift operator matrix, to the power of k times the input signal x. In practice, you want to implement this variant here because it's computationally easier. Here in this case, you have to do a lot of matrix multiplications. Here you just have matrix vector multiplications, which is faster. But both are equivalent, and this one here is sometimes easier to analyze mathematically. So we're going to use this in our analysis. We have an example of this process here on the top where we see a little bit more complicated graph than we had before. And we see that we have a graph signal here indicated in colors, and this size of the circle indicates the signal strength that's present at a particular node. This is the input signal. Now if we apply this shift operator, if we apply s to the power of 0, we get the input signal again. So this is the input signal. If we apply s1, one application of the shift operator, we see how the signal starts diffusing. If we apply it more and more, we see how these large values that are these initial 5 nodes are diffusing over the graph. So with more applications of this shift operator, we're diffusing information more and more over the graph. So now we're ready to define graph convolution filters. Graph convolution filters, as mentioned before, are the basic building block of graph convolution networks. We've seen how such a power sequence defines a diffusion process. And with each k, we have a different state of diffusion. Now we can define this, we can use this to define the graph convolution filter. Given the shift operator s that represents the graph under consideration, and some filter coefficients hk, these are scalars. A graph convolution filter is a polynomial on the shift operator s. So we write the graph convolution filter h of s equals the polynomial, the sum k equals 0 to infinity, that should actually be hk times the shift operator to the power of k. So here we see, what we see here is basically, this is the diffusion, this is the power sequence. This is basically the shift operator to the power of k. And because we can do this for any k, we can define such a sequence. And now the result of applying this filter that we defined through this power sequence to the signal x is simply the following signal, where we have this infinite sum over these coefficients times s to the power of k times the input signal x. What this means is that these filter coefficients, which you can think of similar to the filter coefficients that we have in the kernel of a convolutional networks, but now in this case the filter coefficients determine the importance of a particular diffusion state in this diffusion sequence that we multiply with x. This is what can be learned in such a graph convolution filter. It's different from the filter kernel in a convolutional neural network in the sense that in a convolutional network we know about relative positions. We can associate weights to a pixel in the kernel that's on the top left and on top right. That's not possible here. In this case, on graphs, we're completely permutation. We must be completely permutation invariant. And therefore, we define these filters as weights on this power sequence of the shift operator s to the power of k. Now, the shorthand notation of defining this graph convolution is, or writing this graph convolution is y equals h, and we have the star s indicating that we're having a graph represented by the shift operator s, x. And that's a graph convolution of the filter with the coefficients hk with signal x. Of course, in practice, we're not going to be able to compute this until infinity, so we're going to stop at some k minus, capital K minus 1. We're going to see that. So this is a finite filter. So we've seen that graph convolutions aggregate information from local to global neighborhoods. Let's consider a signal x supported on G with a shift operator s and a filter, a finite filter, in this case h. Then the output of the graph convolution with this finite filter is y equals h convolved, or s convolved with x, is h0 s to the power of 0, which is the identity, x, plus h1 s to the power of 1, x, and so on, times h k minus 1 s to the power of k minus 1, x. So we see that the graph convolution is actually a weighted linear combination of the elements of this diffusion sequence skx, which we have discussed before. We are just performing a weighted linear combination of this skx. Each skx serves as a feature, and we're doing a weighted linear combination of those. We can also visualize this operation using a block diagram. We've seen that graph convolutions iteratively apply a shift, a weighting, and a summation, so we can write it in terms of a block diagram that applies a shift, a weighting, and a summation. So we start with x here, and so we multiply this with h0, and we get h0 times x. And then we add, so we shift the x with the shift operator s, which is s, mathematically it's s to the power of 1 times x. Then we multiply this with h1 and add this to what we had before, which is h0x. And then we shift the signal again. We shift the shifted signal. We get s to the power of 2x, which we multiply with h2, the second or the third coefficient. And then we add it to the output. and then we shift the shifted version of x. We get s to the power 3x. We multiply it with h3, and we add h3 s to the power 3x to the output. And so we get the convolution output of this graph convolution filter. Now, what's interesting is that these graph convolutions, as we have defined them in the most general form, actually capture important special cases such as 1D time convolution. Time convolution is actually just a linear combination of shifted inputs, as we know. So we have this input sequence here on the top, and if we want to compute a time convolution, which we have written down here, this is now the correct notation of convolution, not like the one with the plus that we had for defining in a simple manner convolutional networks. So we have k equals 0 to k minus 1. The filter coefficients hk times xn minus k in this case. So this is just the definition of the regular convolution in 1D. So what that means is that we need to shift the signal, which is happening here. So we see how we shift this signal at location 0 to the first location, second location, third location, and so on. This is indicated here by this shift operation. And so we're shifting the input signal and multiplying the shifted signal with h after each shift. And then we're adding it to the previous output, similar as before. And we do this multiple times to arrive at the time convolved output. This is just a regular time convolution as a block diagram. Now the question is, can we express this time convolution via a graph convolution? And what should the graph be? Well, the answer is yes, we can. If we consider a simple line graph where we have node 0 influencing node 1, node 1 influencing node 2, so there's an edge from 2 to 1, and there's an edge from 3 to 2, and so on, then the corresponding adjacency matrix of that graph, assuming an unweighted graph, is this one here. Imagine this matrix extending all the way to infinity to properly define the convolution, but here we're just looking at a 5 by 5 crop of this matrix. The important thing about this matrix is that it has zeros everywhere, but it has ones just below the diagonal, which means that if I multiply an input vector like x0, x1, x2, and x3 with this matrix, then I obtain a shifted version of that vector, because I have these elements just below the diagonal that are basically permuting the input vector in a way that every element goes to the next location. So we have x minus 1, x0, and x1 and x2 at the locations inside that vector where we had x0, x1, x2, and x3. And again, imagine these matrices and these vectors to extend to infinity in both directions here, like in previous time and in future time. So we have found a shift operator, a very simple shift operator that is allowing to realize regular time convolutions as a special case of graph convolutions. And so we can use our standard block diagram here again from before, where we have the shift operator now that shifts the input, and then we multiply with the coefficients h. In other words, time convolution is a polynomial on the adjacency matrix of the line graph and can be expressed using the same graph convolution operation that we have defined before. Now, if we let the shift operator be a shift operator of an arbitrary graph, not just a line graph, then we recover our more general graph convolutions again. So this is a general graph that we see here, where these little dots here, the height of these dots, indicates the value, the signal at each node. And then we can do exactly the same thing as before, but now on a general graph. Now, one last word on graph Fourier transform. So this is also a bigger topic on its own. So I just want to mention it on one slide briefly. Graph Fourier transforms are the equivalent of standard Fourier transforms, but now for graphs, and they are an important tool for analyzing graph information processing systems. Given an eigendecomposition of the graph shift operator, so we have the graph shift operator S here, and this eigendecomposition into these three matrices here, the graph Fourier transform of the graph signal is given by the projection of the graph signal X under consideration onto the eigenspace V star of the graph shift operator S. So we have a very simple way of obtaining the Fourier transform of a signal by just projecting it onto the eigenspace of the graph shift operator. And the nice thing about working in the Fourier domain is that similar to the regular Fourier domain for the Euclidean domain, is that graph convolutions are pointwise in this Fourier domain. So we can then, like this whole convolution operator becomes a pointwise operator. So we have a pointwise multiplication here. Now, yeah, this is a bigger topic, as I mentioned, and if you're interested in this topic, I encourage you to have a further look into for instance, this lecture that I link here. So I want to leave it for this lecture. We're going to leave it with this, just this little overview of graph Fourier transforms, which are the equivalent of Fourier transforms, but for graphs.